Hello everyone and welcome back to Nunley Math. Thank you so much for joining us here today as we continue our discussion of linear patterns, linear equations. We're going to do this just a little bit differently today. Today we're going to take the more geometric approach to our examination of linear patterns or linear functions. So let's look at this. Suppose you own a reception hall that you rent out for graduation parties, wedding receptions, and other events. The number of people you can seat at a table is directly related to how many tables you set up side by side. The figures below show what the first few arrangements look like. Find the relationship between the number of tables used, x, and the number of people that can be seated together, y. How many people could be seated at 10 tables arranged like this. So here's the first table. It looks like this. You've got one square table and you have one person sitting on each side of the table. When you add a second table, it looks like this. A third table and a fourth table. And we want to use this as our template or our pattern so that we can say as long as this same arrangement of tables and chairs continues, we should be able to predict for any number of tables how many chairs or how many people we can put around them. So let's start with table number one. We already said table number one has 1, 2, 3, 4 people seated around it. Table number 2 has 1, 2, 3, 4, 5, 6 people seated around it. Table 3 is 1, 2, 3, 4, 5, 6, 7, 8 people sitting around it. And table 4 has 4 on top, 4 on bottom. That's 8, 9, 10 people seated around it. Now, just like in the last video, I want you to pause for just a second and think about what patterns you might see. If you remember the last video, you may want to even pause this and try and write the entire equation or function on your own. I'm going to assume that if you wanted to do that, you already have, and I am just going to keep going. The first thing we want to do is look for what patterns emerge. Hopefully you realize, I'll go ahead and add 5 and 12 in there. Hopefully you realize that we are growing by 2 people every time we add another table. Every time you add a table, you can increase your seating capacity by 2. Now, unlike what I did in the last video, I'm going to start with that information first, this constant rate of change, because you can see I am repeatedly adding 2 people. So if I want to relate this back to the number of tables, what I would say is that every time I add a table, I add 2 extra people. So if I have one table, I'm able to increase my capacity by 2. If I wanted to add a second table, I increase it by 2 sets of 2, 3 sets of 2, 4 sets of 2, and 5 sets of 2. This is our constant rate of change. This is how many tables we've put in, because we said every time we add a table, we add 2 people. Now, most of you are probably already thinking, wait a second, this doesn't make any sense. 2 times 1 doesn't equal 4. 2 times 2 doesn't equal 6. 2 times 3 does not equal 8. 2 times 4 does not equal 10. And 2 times 5 does not equal 12. These are all, in fact, incorrect. But they are all incorrect in the exact same way. Do you know what that is? If I want to predict how many people can sit at any number of tables, I'm going to say, well, it's 2 times the number of tables, or I get 2 people added on for every table, but there's also an additional 2 people at each table. Notice 2 times 1 plus 2 equals 4. 2 times 2 plus 2 equals 6. 2 times 3 plus 2 does equal 8. These were all incorrect by 2. So my pattern is 2x plus 2. The question becomes, how did I figure that out? I mean, I could make a table like this, and I could just realize they were all off by 2, but this 2 and this 2 both have very specific meanings in this problem. The 2 over here on the left in front of the x, this 2 right here, is how fast I'm growing. I'm growing by 2 every time. But for some reason, there are 2 extra people that I have to take account for in this problem. The easiest way to see that is to look at this transition between 1 table and 2 table. When you look at this, What's the difference between here and here? What changed? What was added on? Where are those 2 extra people? Well, hopefully you can see that these 2 people are new. This person already had a seat. This person already had a seat. This person already had a seat. And this person already had a seat. When I added this table, the only thing I did was I increased the capacity by these 2 people. Those are your extra 2. Everybody else already had a seat. And in fact, if I were to continue this pattern to the third example, these people right here are the 4 people that originally had a seat. We added 2 people here, that's these 2. But these 2 people are new. When I added the third table, I was able to add on this extra group of 2. And when I come over to 4 tables, I still have these guys who originally had a seat around the original table. When I added a second table, that's these 2 people here. When I added a third table, that's these 2 people here. And when I added a fourth table, well, that's these 2 people right here. Notice that at table 4, I have these 2, these 2, these 2, and if I look at these 2, I have 4 groups of 2. That's what this says right here in the chart. 4 groups of 2 plus 2 extra. Table 3 had 3 groups of 2. Do you see them? 1, 2, 3 groups of 2 plus the 2 on the ends. This is 2 groups of 2 plus the 2 on the ends. So when I get to table 1, what really is happening at table 1 is we're saying this one table provides for 2 people plus the 2 extra on the end. In fact, if I were to go backwards 1 stage and I were to look at the 0 step of this problem, you could see that this says that if I had 0 tables, I would still have seating for people on the ends. Now that doesn't make any sense, and if we were being really formal about this, we would limit our domain and say that our pattern only works for 1 table or more. But it does illustrate an interesting point. The people on the ends always have a seat. That's these 2 people right here. But every time you add in an extra table, you add an extra set of 2 that could be added to the top and the bottom. Now, that's probably a little overwhelming. I've got a lot of lines drawn here. I'm going to erase those just real quick. And we're going to look at this. We're going to look at this as a linear equation. Notice, linear equations say y equals, for this problem, 2x plus 2. Or if we wanted to call it a linear function, we would just use f of x instead equals 2x plus 2. Remember in the last video we said f of x and y mean the same thing. It's just a question of which method we want to use to write that. But a linear equation or a function always has some initial starting value and some constant rate of change. Notice we assign that starting value the variable b and the rate of change we call m. In this particular problem, this pattern starts with the 2 chairs on the end. That is our B. And then we add an extra pair of chairs on the top and bottom every time a new table is added. So this is 1 set of 2. This is 2 sets of 2, 3 sets of 2, and 4 sets of 2. As we get better and better at this, we can look at pictures and read stories, and we can find this starting point and rate of change much more quickly. I'm going to erase all this for just a second. Let's try another one of these. By the way, the question did ask us how many people could be seated around 10 tables. We rewrite the original formula. Since x is the number of tables, I plug 10 in for x, and we solve to get 22 people. Let's take a look at another one. This is the rocket pattern. You're building the pattern below using geometry tiles. So this is rocket 1, this is rocket 2, rocket 3, rocket 4, and rocket 5. It says, write a function that describes the total number of blocks or tiles needed, that's y, to build figure x. That's the rocket. What's the largest figure you can build with 100 blocks? So take a look at this rocket real quick. Remember, whenever we talk about linear equations, we're always looking for a starting point and a constant rate of change. So let's look at how many blocks it takes to build the first rocket. 1, 2, 3, 4 tiles. Rocket 2 is 1, 2, 3, 4, 5 tiles. Rocket 3 is 1, 2, 3, 4, 5, 6 tiles. And rocket 4 is 3, 4, 5, 6, 7 tiles. And rocket 5 is 1, 2, 3, 4, 5, 6, 7, 8 tiles. Rocket 5 is 8 tiles. Now, hopefully, you're good enough that you can look at that and realize what your rate of growth is. This is changing by 1 tile every time. In fact, if I wanted to, I could say, well, I'm repeatedly adding 1. So rocket 1 has 1, 1. Rocket 2 has 2 1s. Rocket 3 has 3 1s. Rocket 4 has 4 1s. Rocket 5 has 5 1s. And in fact, we could look over here, and if we were trying to figure out where this plus 1 is coming from, you ought to be able to look at this and realize, well, rocket 1 has 1 plume of smoke. Rocket 2 has 1 plus 1. Rocket 3 has 3 1s. Rocket 4 has 4 1s. And rocket 5 has 5 1s. Notice that's what it says here. 1 1, 2 1, 3 1, 4 1, and 5 1. Every time your rocket increases, or your rocket number increases, you are doing plus 1 plume of smoke. But notice, none of these equal the number of tiles they're supposed to. 1 times 1 does not equal 4, 1 times 2 does not equal 5, 1 times 3 does not equal 6, 1 times 4 does not equal 7, 1 times 5 does not equal 8. But when I go to set this up, I do know I'm growing by 1 every time, and I also know these are wrong by the exact same number. All of those need a plus 3. So there's our function, y equals 1x plus 3. Now, if you look over here, you can probably see why each of these needs 3 extra tiles. Well, hopefully you know, the 3 extra tiles are used to build the rocket itself. This is a great illustration for us of the difference between this starting point, this plus 3, and this constant rate of change. I start with 3 tiles to build my rocket ship, and then I increase by 1 plume of smoke for each increase in the rocket. Well, how could I get this number 3 without having to go to all this trouble? Well, if we were to go backwards, you could see that 0 tiles, or I should say a rocket ship of pattern 0, or the rocket that would be in position 0 over here, would be the rocket with no smoke. This rocket 0 would fit into the pattern. So if we want to know the formula for this function, we have our starting point, or what would the rocket what would the rocket look like before stage 1? Where do we start with before we start adding plumes of smoke? Plus whatever our rate of change is. Tell you what, let's take a look. If a linear equation of function has a starting point and a constant rate of change, that means it's going to fit the form y equals mx plus b, m being our rate of change and b being our starting point. Well, if I go and plug in my values, 1 is my rate of change, because I'm growing by a piece of smoke every time. But 3 is my starting point because I needed 3 extra tiles to build the ship. I'll always have those 3 tiles. Those always stay constant or the same. What changes is the plumes of smoke. So this question is, what is the largest figure I could build with 100 blocks? Since 100 blocks would be 100 substituted in for y, I plug that in and use my property of equality to find that I could build rocket 97. Here's an interesting example, the hexagonal sun pattern. You're building the pattern at the left using geometry tiles. Write a function that describes the total number of blocks y needed to build figure x. What is the largest figure you can build using 500 blocks? So let's see, here would be figure 1, figure 2, and figure 3. So I go through, our goal is to create an equation or function that represents the relationship between the figure and the number of tiles needed to build it. So figure 1 over here on the left has 1, 2, 3, 4, 5, 6 red tiles and 1 yellow hexagon for a total of 7. The second figure, figure 2, has 2, 4, 6, 8, 10, 12 red and 1 yellow. And then we have 3, 6, 9, 12, 15, 18 red and 1 yellow. Hopefully you can see that we are growing by 6 each time, which means that figure 4 will likely have 25 and that figure 5 would likely have 31. Since my constant rate of change is 6, I would write this as 6 times x. So every time our figure gets bigger, it gets bigger by a factor of 6. In fact, I could actually go through here and let's see if I can grab this. There you go. I can actually go through here and I can see that what's happening here is I start off with one set of 6, then I have 6 and 6. I have 2 sets of 6 in figure 2. I have 1, 2, let's see if I can get this drawn correctly, and 3 sets of 6 in figure 3. So when I put in a figure 1, I have 1 set of 6. Figure 2 is 6 times 2. Figure 3 is 6 times 3. But all of those are incorrect. 6 times 1 does not equal 7. 6 times 2 does not equal 13. 6 times 3 does not equal 19. 6 times 4 is not 25. 6 times 5 is not 31. In fact, they're all wrong, but they're all wrong in the exact same way. Why is it that when I take one set of 6, that's not the number of tiles needed? Well, because you have this one yellow tile in the middle. You see, what this pattern or formula is saying is that we are going to add a circle of 6 squares every time, but if we think backwards and ignore those 6 red tiles, there's always one extra yellow tile in the middle. We could call this y equals 6 times x plus 1. Notice you have one yellow in the middle and you have a ring of 6. So 1 ring of 6, 2 rings of 6, 3 rings of 6. The 1 is constantly there. It's always there, and if in fact we went back to a stage 0 where we got rid of this last ring of red, you would still have that yellow hexagon in the middle. So if a linear function says that any pattern has a starting point and a constant rate of change, and that's described as y equals mx plus b, we would say that the rate of change or the rate of growth here is 6. That's the 6 square tiles added on repeatedly. The b then would be the starting point, and that is the one hexagon in the center. So this pattern y equals 6x plus 1 describes this relationship. Now, if I want to figure out how many or what figure I could build with 500 blocks, I would just plug 500 in for y because y is the number of blocks or tiles. I'm going to subtract 1 from both sides, divide both sides by 6, and I get 83.16. Since I can't build 1/16 or 0.16 of a tile or of a figure, I would say the biggest I could build is figure 3, 83. I have enough tiles for figure 83, but not enough for figure 84. Again, I'd recommend you pause this and try this on your own. This is the triangular toothpick pattern. Notice that we are looking for the pattern between the number of toothpicks, this should be y, compared to the figure number, which is x. I switched my variables there. In this case, figure 1 requires 3 toothpicks. Figure 2 requires 5 toothpicks. Figure 3 requires 7 toothpicks. And you can see it's growing by 2 every time. That means figure 4 is going to need 9, figure 5 is going to need 11, and then figure x is going to need 2x, because apparently we are growing by 2 every time. In fact, you can see that if this is figure 1, I'm going to grab my highlighter, if figure 1 is these 3, 1, 2, 3, to build figure 2, I actually have to add on 2 more, 1, 2. And in fact, if I compare figure 2 to figure 3, you can see what I add on is 1, 2. Every time my figure gets bigger, I'm going to add 1, 2. In fact, I could go through here and I could take my pen and I could draw figure 4 by adding 1, 2. I could draw figure 5 by adding 1, 2. It's funny because we think of triangles as adding 3 sides, but that's not actually what's happening. And the reason for that is because, there we go, is because when I'm adding something on, I always have one side of the new triangle already given. This side right here is part of this triangle. This side right here is part of this triangle. All I'm doing is adding 2 extra sides to make the new figure. So, if we know all of these are wrong, we're adding 2 every time. This is 1, 2, which is not a 3. This is 2 2s, which is not a 5. 3 2s is not a 7. What we need to do is find out what would happen before I had any 2s at all. Well, something plus 2 equals 3, that must be a 1. In fact, if I were to follow this figure backwards, removing these 2 would leave me with figure 2. Removing these 2 would leave me with figure 1, and in fact, if I were to go back to a figure 0, it would just be this line by itself. So you've always got to have that extra line to build that first triangle, but then every triangle after the first triangle is just going to need 2 extra sides. That's what our formula says. It says, hey, you need 1 extra side on your first triangle, but after that, every triangle is going to have 2 sides. So figure 1 would have 2 sides plus the 1 extra, that's 3. The next one you would have 2 extra, or you would have 2 more plus the 1 from the initial figure. If a linear function has a starting point and a constant rate of change, or y equals mx plus b, my constant rate of change is the 2. That's the 2 extra toothpicks every time. You can see a little cutting and pasting error here. Toothpicks every time. And when we go down to b, we have that plus 1 because we have that 1 extra toothpick on the first. The 1 extra on the first. That's where this equation comes from. It's always starting point and a constant rate of change. So if I want to know how many toothpicks I would need to build figure 80, the figure number is the x. The number of toothpicks then would be 161. 161 toothpicks. Now, these don't have to be geometry applications, but I like to start with a geometry because it helps me to see visually what the pattern is, and that is the starting point and constant rate of change. I could do this with other problems as well. Give the relationship between the number of weeks that pass and the number of days. Well, I could say that as it's 7 days every week, but there's no additional value needed. Or if I were to say to you, Dawn has 25 tickets and she thinks she can win 5 tickets every minute, I know that she initially had 25 and she's gaining 5 every minute. My rate of change is 5, my starting point was 25. Joe has already run 7 miles, that's our initial value, and he's running 0.2 every minute. That's my rate of change. We start with an initial value of 7, and our rate of change is 0.2. You might want to consider trying this next one on your own. It is a little bit different. See if you can work your way through that. I'm going to keep going, assuming you're already doing that, or you've already done that if you wanted to. We start with $45, but we, be careful, spend $2 every day. Spending is negative. So my starting point was the $45. My rate of change is down to every day. Remember, this multiplication is the repeated addition or subtraction. Josh is in debt 15, but earns, that's increases $2.50 per hour. That's what he starts with. This is his rate of change. That's starting with a debt of 15, that's negative 15, and your rate of change is 2.5, or he's getting out of debt or gaining $2.50 every hour. Notice if he works for 2 hours, he's gained $5, and now he's only in debt 10. Be careful, I got in a hurry there, and I almost skipped over the word debt. Good thing I made the slide in advance, and it had that negative sign on there for me. You don't have that advantage, so please be extra careful. You have $50 to spend on prizes. That's what you start with. The prizes cost $2.50 each. So we have $50 and we're spending $2.50 for each prize. Well, that's negative $2.50, or we're going down, but we started with positive 50. This is going to be really helpful for us long term. This idea that we can think starting point and rate of change, and as long as the rate of change is constant, we can create a formula or an equation without doing a table. We're going to do a lot of that over the next several days. I hope this has been helpful to you. As always, we do appreciate you joining us here at Nunley Math. If this was useful for you, make sure you give us a thumbs up. Make sure you turn on your notifications by ringing the bell so that you can receive an announcement anytime we do something new here at Nunley Math. As always, we wish you the very best of luck. You guys take care of yourselves. Bye-bye.